So we continue. So coming to the point where we just have these finite dimensional vector spaces, how we can have the analytical analysis part of it, how it interfaces the analysis or the convergence or the sequences, how we study them in the analysis part of the things, how we can relate with finite dimensional spaces or infinite dimensional spaces. To begin with, the analysis part of it is that how can have a convergence of vectors, like the way we study in the real analysis we study sequences, which may be a convergent sequences or a divergent sequences. So if there's a pair of this thing, if there's a pair of this conjugate elements, how we can define the convergence of series sequences, but in the context of how we can construct those bases in finite dimensional space, or define how we can see them in that context. So we have been aware of normal transformations and mostly inner product spaces, which came in a particular cases peculiarly when we introduced complex vector spaces. The inner product spaces were defined in that sense, which had a certain norm. So how can study the study of convergence properties that arise properties that arise from in an inner product space. So this is our thing, that how we can study convergence properties which arise from these inner product spaces, which were particularly constructed from how we define complex vector spaces. That's one. Now, what we say, we have asserted that a sequence xn of vectors in V converges to a vector x in V. So there are two possibilities to suggest. For example, xn minus x tends to 0 as n tends to infinity. So you can have a sequence where this will tend to 0 at the moment this n can take values 1, 2, 3. So the difference of the two should go to 0. The larger the n becomes. So, or further, we can define it xn minus x of y tends to 0 as n tends to infinity for fixed y in vector space. So we have, if we fix y, this tends to 0 for any fixed y in C. So we can fix it in that sense. So the point arises, so if 1 is true, if the first is true, we have for every y, we have for every y xn minus x into y, it's less than or equivalent to mod of. So you can have it, this property, you can just shape it. So xn minus x or this thing. So this property can be so this is true from second. This is true from second. So in a finite dimensional spaces, the converse may be true. From this, you can go to this. First, you can define this as a true, and from that, you can just arrive at this thing. So to prove that you cannot the logic goes this way, you define things this way, and then you can arrive at this way. The thing is that if we have let Z1, Zn be an orthonormal basis, be an orthonormal basis, then basis in a finite dimensional space V, then and we reserve n for the dummy variable as a limiting process. You can see n is a dummy for the limiting process because the sequence may somehow can be bounded from above or below. So such that so if we assume that second xn minus z xn minus x into zi tends to 0 and I goes to 1, 2, so on and so forth. Zi or y is normally fixed. So from theorem 63, so we have the logic of if you go to section 63, so section 63 so there are, for example, if you read the sections, we have just shown if chi is an finite orthonormal set in an inner product space, the following six conditions are equivalent. Orthonormal set chi is complete. If xi is 0, then this is this. So the logic of this is also the subspan spain by this is this thing. So we can look at theorem 2. Theorem 2 section 63. From that, the logic of that, one of this thing is that is equal to xn minus x zi square. So it follows that xn minus x tends to 0 as was to be proved. So the argumentation goes basically that we start the sequence xn minus xn, where the other is this thing. Here we normally have bounded it, we replace it by zi, and from the logic of this theorem we can say this is equal to this. So from this you can just say the validity of this is there. So if you want to, we normally had a scalar and a vector, alpha n and x or beta of y, how we constructed these finite dimensional vector spaces. But here the alpha and beta can be replaced by alpha n and beta n, and where n can go from 1 to n or whatever. So those scalars or those vectors, so we can have those scalars or those vectors, if you remember. So I'll write it from this side. So those scalars, so alpha n can move to alpha, beta n can go to beta, xn can go to x, and yn can go to y. That's fine. Such that alpha n xn plus beta n xn. So it's the multiplication of scalars and vectors in those vector spaces, the addition of it. So for typically it can go for if x is 1, so you can write it like this. In the sense that if x n goes to x and alpha n goes to alpha, so you can this can be written as this. So it's not mentioned that it's basically this can be a sequence of what I should say, spanning that orthonormal set, or sorry, orthonormal basis. Not to mention orthonormal basis in V, which so the notion of convergence coincides with the notion of so here from this the notion of convergence can be similar or it coincides with how we define n-dimensional real or complex vector spaces. So the sequences, the idea of sequences, how can incorporate them in the way we define the scalars and vectors, the addition of two elements in given vector spaces. So we only have to replace this n for a particular case. So the notion of these sequences and convergences can be incorporated as an idea. That's it. So in that sense, so for a particular case, for example, Lxn minus xm tends to 0 as n and m tend to infinity. So it's sort of convergent sequence becomes the same way. If n and m tend to infinity, this sequence converges to 0. So this is the way we can define it for the simple case. Now comes how define how can we define how can we define the norm of this thing? How we can define the norm? Norm. So norm, the definition of it, if you want to define the norm, definition of norm goes like this. So a linear transformation, A on an inner product space, B is bounded if there exists a constant K such that Ax is less than or equivalent to K, or for every vector x in V. So the greatest lower bound of all constants is, so the greatest lower bound. So if you remember in the language of real analysis, we called GLB or ULB. For the upper lower bound or the greatest lower bound can be the greatest lower bound of all constants K with property of norm or bound of A is defined as, is not defined, is denoted as by modulus of A. So this is the way we have defined. We're going to define So we're going to define things. So a linear transformation A on an inner product space V is bound if there is a constant K. And constant K should exist such that this, the way we define this amount of this, it should be less than or equivalent to Kx. For every vector x in V is a finite dimensional space. So the greatest lower bound of all constant K with this property of norm bound by, so it's bounded by norm by A. It's denoted by modulus of norms. So if it's defined that way, so from this you can see modulus of Ax is this property should hold. So if you have rehash our previous, the way we define Cauchy's inequalities and Schwarz inequality, so you can say the logic of it can be justified. From the, if we may consider the non-zero perpendicular projection of an isometry, so you can go to section 5 and to justify it. So if P is the possible property, P is possible properties of, if P is possible property of real numbers T, we shall denote set of all real numbers T possessing the property P by this symbol, and we should denote the greatest lower bound and the least upper bound by the infimum for infimum, and for a supremum we can define as supremum. So we have modulus of A can be denoted as infimum of K such that modulus of Ax is for all x. So we can define the point is in the that given sequence in which we have defined this norm. So we have to define the upper bound as well as lower bound for the given sequences. So for an particular infimum or a supremum, so if you want to define it this way, the infimum, so it should be less than or equal to this bound K of x for all s. So the notion of boundedness is, in a sense, closely related to the idea of continuity. The way we define that epsilon delta definition analysis for two sequences. So if A is bounded, and epsilon is any positive number, so by writing delta in terms of epsilon and in terms of this mode of A in that given sequence, so we can define it. So, and making sure that x minus y is less than delta. So from this, it implies, or you can argue that ax minus ay, modulus of ax minus ay, sequence of two numbers x and y, or you can say a of x minus y can be greater or less than or equivalent to modulus of A, modulus of x minus y is less than epsilon. So from this you can say in a sense that boundedness should imply continuity. Boundedness implies continuity. So in an indirect way, we have used the epsilon definition delta of the limits, and so if it's if it lies, for example, a linear transformation A on inner product space it is bound if there exists a constant K. So we have defined a linear transformation A on inner product space, which should lie within bounded within a certain constant. And if we introduce this epsilon and delta definition, epsilon and delta can be defined in this way. So we can introduce notion of continuity in our idea of how we define these inner product spaces. Or how we can indirectly say the boundedness should imply continuity. So from this, you can have a theorem which says that the theorem, if I state the theorem states that so every linear transformation on a finite dimensional vector space on a finite dimensional, because here we are interested in the inner product space. The inner product space can be complex, is complex. In a finite dimensional inner product space, space is bounded. It's bounded also in that sense, in the general sense. So the proof is also in a sense simple, it's not that complicated. So we are going to use the argumentation, again in the previous argumentation. So if we assume that the proof assumes that, for example, proof is that, so if we have a linear transformation B, such that and x1 so on be orthonormal basis in V. So we can write K naught, which was previously the constant, the bound. We can write it as maximum of AX1, AX2, so on and AXN. AXN. So since arbitrary vector x may be written as x xi. So we are going to invoke the notion of Schwarz inequality here. From Schwarz inequality, if you remember that modulus of xi is 1, so we can define E of x. E is the linear transformation, can be defined as E times sigma I xi. So twice wide. So again, we are going to invoke the inequalities here. You can further say this can be written as, you can write it further as, put it here and just xxi, exi. Further, you can have an inequality where this is less than this, and further this inequality can be written as xi of xi is less than or equivalent to P of x, or it will be further equivalent to n of K naught of x. In other words, so K we have defined here, Ki. So K we have defined here as this. So you can reduce this as this from this. You can say yes, yes, yes. So in other words, we have defined K as and K naught. A is bounded of A, and so the proof is complete. So the proof is very simple. We have only used Schwarz equality here to define this in this. And from this you can see every linear transformation of finite dimensional product space is bounded. So the notion of boundedness is emphasized here. So the point is how we can express norm in different ways. So the way we have a sequence which can converge or diverge from a given bound. So how can, if there is an Hilbert space, how you can define its relation vis-a-vis that bound, the symbolic expressions, how we can or notationally use them. So expressions of norm, that would be the proper. The way book has said, the expressions of the norm, expressions of the norm can be. So I'll only write it so that it later will help us in how we can construct those boundedness of this linear transformation or this inner product space. To facilitate the working of norm for this transformation, you can consider the expressions. This is supremum of, if you just recall your thing in real analysis, such that x is not equal to 0, or q can be defined as supremum of is 1, and r can be defined as supremum of axy. Sorry, where x is not equal to 0 and y is not equal to 0. Or x can be equal to 0, or x, for the other thing is we can also define it as axy. We can define it x where the modulus of x, modulus of y is 1. So here we have to remember this modulus of this it's a brace notation, which means that set of all real numbers of the form this modulus of x are considered for all x's, for which modulus of x is 1. So we can use this, you can look towards this thing, you can use, or I'll just, for example, so ax is less than or equivalent to kx is trivially true. Why it's trivially true? If k is bound, it will always be come within the bound. So true in any k if x is 0. So if it's trivially true. So the definition of supremum will imply p is equivalent to modulus v. So this is the different ways in which these boundaries have been defined. For example, I just write two properties. For example, a of xy modulus of y can be written as ax prime y prime. If x is not equal to 0 and y is not equal to 0 for this case, or If P is equal to Q is equal to A, we can define AX of Y as this inner product as less than or equivalent to AX of AY of X of, sorry, this is Y. So Y and Y cancel, so you can say AX by Y. So X by X, sorry, Y and Y. So you can say these are different ways of how you can notationally write. Or the other property is this mod of X can also be written as AX by mods of X, mods of Y. So these are different ways of notationally how we can symbolically represent them. And if you remember, there are a couple of properties which we have been using throughout these finite dimensional vector spaces that we will define this additional property. So you can extend those properties in that sense here also, that if the numerical functions of the transformations, numerical function of transformations satisfies the four conditions such that A plus B mods of A plus B is less than or equivalent to mod of A plus mods of A of B can be less than or equivalent to mods of A mods of B. If you have a scalar, you can just get scalar out of this thing. You can write it like this. And this, the conjugate of this thing is equivalent to, you can write it like this. But normally for adjoint transformation, you can have it. The point is that if the function of transformations are defined this way, can we write it? So the first three is fine. The fourth one, can we write it this thing? The proof of the fourth is in the way simple, in the sense that if you just see the if you see the book, if you see it, so the fourth proof, the first is, so you can have these three. The fourth one can be shown to be, since if we define it, the inner product X and Y are the elements of that norm. So you can also write it, if you just flip it, you can write it also as properties of linear transformations as A conjugate Y, and further from this property inequality, you can also write it as A star Y. So it's less than or equivalent to A star. Again, we are going to just from this you are going to use this property here. So you can have this X of Y. So again, modulus of A star can be less than A star. So we are going to replace A star, A by A star, A star by A star star. It will come back to A. Conjugate of this complex conjugate of conjugate will come the element back. So we can obtain the reverse inequality. So in a way, sort of correlative, we can define it. Now the other thing is that the way we can also have what I should say, how we can define how we can define the bounds of bounds of self-adjoint transformation, bounds of self-adjoint transformations, which are linear transformations in that sense, or which are those transformations which are defined within as a sequences which may be convergent vis-a-vis that bound of those inner product spaces. So what can be the bounds of those self-adjoint transformations which we have been? So within which those sequences should exist. So if we consider, so if you follow the book, we'll take a special case of transformation rather than just general. So we can always go for special, then go for general. So if you say phi of x, phi is defined as Ax, phi is defined as A of x, x square, x not equal to 0. The other psi, we define phi and psi as this. So one is defined this way, and the previous notation, the other is this way. Just define this. And further, we can define for x not equal to 0 and y is modes of x and y is 1. So we can define ax mod of x square is equal to ayy. So if you define your things this way, we can write alpha and beta in terms of alpha as infimum of phi and beta as supremum of phi. So infimum of psi and supremum of psi, where alpha is the upper bound, this is the upper bound, and this is the lower bound of that of the self-adjoint transformation A, for which that inner product space is defined. So greatest real number can be A minus alpha, can be greater than 0, or we can have beta minus A is less than or beta minus A or is greater than or equal to 0. So beta minus. So you can also have basically, if you flip it, it can be less than or equal to 0. So if you say it's A minus beta, then it will be less than or equal to 0. From this, you can say upper and lower bounds. So to get it both of, so it will look the same. And considering the numbers, gamma can be defined as maximum of alpha and beta in this sequence is defined, maximum is defined as. So half of the proof is easy. So if you define things this way, so it will always be less than or equal to the way we have been doing it. Ax is less than equal to is less than or equal to modes of A into modes of x square. So it's clear that alpha and both beta are dominated by mod of A. Alpha and beta are dominated by mod of A. So now we can have to prove the reverse inequality, we can the way we did in the previous thing. So we can have gamma minus A and gamma plus A. And the proof, we can conjugate the two and you can say it, write it only. So gamma plus A star and gamma minus A, gamma plus A. So the other one can be defined it. If it's gamma plus A, the other can be defined as gamma minus A star. The two bounds of the two sequences, gamma plus A and gamma minus A, can be defined as gamma plus A and gamma minus A. So we flip the signs. So this is equivalent to, this can be equivalent to gamma plus A, gamma minus A, gamma plus A. This is equivalent to gamma minus A, gamma plus A, and gamma minus A. So are positive. So we can have some, where some together inside that gamma square minus A square. We can do some algebra with these two expressions. They define the upper and the lower bounds of the given sequences which are bounded by this A. So the gamma square minus A. So you can have, if you just simplify it, square minus x square gamma square as an inner product of these two elements is always greater than a square x x, or it's equivalent to. So it's also a proof which is complete, where gamma as a sequences, and the proof is complete in that sense. So proof is complete in the sense that how we can define the bounds of the self-adjoint transformations, which are defined by certain this thing and bounded with these two elements, where the supremum and infimum are defined in terms of alpha and beta. And using this identity, we can show that how we can define the bounds of the self-adjoint transformations, which are defined by these with these inner product spaces. Now the last thing which we will stop here is how we define minimax principle. Minimax principle. So the so it's a principle which is also somehow related to this self-adjoint transformations. Self-adjoint transformations, which we define, which are part of those inner product spaces, or which are those transformations which are bounded from above or below. So the theorem says that let A be a self-adjoint transformation, A be a self-adjoint transformation on n-dimensional inner product spaces, on n-dimensional inner product space, and lambda 1 and so on, and lambda n be not necessarily distinct. Then proper values of A, proper values of A with the notation chosen such that lambda 1 is greater than or equal to lambda 2 is greater than or equal to lambda 3, so on, is greater than or equal to lambda n. So for each subspace M, of B, so we can define mu of M for each subspace. We can define one of the supremum can be defined like this. This is inner product space such that in M subspace modulus of X is 1. For K is 1 and N. And the infimum can be defined as mu K. For this subspace, the infimum can be defined as mu of dimension of n such that it's equal to n minus k plus 1, where mu k is lambda k and k goes from 1 to n. So we can say, so I'll just repeat what the theorem says, that A be a self-adjoint transform of an n-dimensional space. So if it's an self-adjoint transformation of n-dimensional inner product space, and these are not necessarily distinct, they can have different values, or these with these property. So if we define it lambdas in this way, so for each subspace, so if we define them as part of this consecutive this thing, which are not necessarily so if we define these lambdas like in this way, so for each subspace, supremum can be defined like this way, and in the infimum, the dimension of this infimum is defined like this. And k goes from 1 to n, and mu is lambda n. So proof, I'll just let it be. So proof is again so maybe I will just only state it in the next class. We're going to just see it. So we have this stated this result. So we'll just continue from this in the next class. So stop.